Hello, my name is Martin Blunt, and in this series of videos, I will be going through the course, The Fundamentals of Oil and Gas Engineering. And these first couple of lectures, I'll be using slides. So what I will do is I'll put the slides up on the screen now. So there are the slides, the title, Fundamentals of Oil and Gas Engineering. My name, Martin Blunt, and I got there my email address, and that is, in fact, the best way of contacting me. So I'll give you a little bit about my background. In fact, my degrees are in physics from Cambridge University. After I got my PhD, I worked as a reservoir engineer for BP in England. And then after that, I became an assistant professor in the Department of Petroleum Engineering at Stanford University in California. And for the last 20 years, I have been a professor of petroleum engineering at Imperial College London. And since 2012, I've also been a visiting professor at Politecnico di Milano. I'm teaching in Milan as well. So I'm available to answer any questions that you might have about the class. But I would recommend that you do contact me primarily using my Imperial College email address that's given there. The course obviously is in English. And we also have an assistant for the course, San, who has a PhD from Polytechnic. In terms of the assessment for the course, there will be a written examination plus one piece of assessed work. There will not be a formal oral examination for this course. So the first thing is, well, where do I get a little bit more information on this course? I have the notes that are available online, but there are also two books. The first book here, Multi-Phase Flow and Permeable Media, this is more a research textbook that contains some of the background to some of the material that we're going to teach, but it isn't really the textbook for the class. The second one, which is part of the Imperial College lectures in petroleum engineering, one volume on reservoir engineering, that essentially is the textbook for most of what is in this class. This book you can buy, but if you don't want to do that, it's published by World Scientific, the lecture notes that I have online essentially follow the same material as this book. So those are really the two references for this course. So the style will be formal lectures, here given by video, and there will also be examples classes to go through calculations, engineering calculations associated essentially with reservoir engineering. So I do invite questions, obviously impossible to do over a video, but we will arrange for people to be able to contact me and ask questions if there's anything about the course that you don't understand. As I said, the assessment will be a written examination plus some assessed work that you do in your own time. You do that individually in your own time, and you do one of them. As will become clear in one of the later lectures, we'll do a little analysis of so-called peak oil, the population and other things, so you could do your own analysis there. Or you could do last year's examination, or right at the end of the course, when we talk about spontaneous inhibition, that's rather more mathematical, you can do some calculations there. What I've shown in bold is last year's examination paper, because in the end, most people simply do last year's examination paper because it's good for practice. So the outline for the next couple of lectures is going to be an introduction to what the oil industry is all about, petroleum exploration and production, and also an analysis of fluid pressure regimes. So those are going to be the first two lectures. Then after that, we're going to start tackling some big problems, or at least perspective on some of these big problems, looking at population, climate, and oil resources. In terms of the whole lecture course itself, these first couple of videos will be simply introduction. Then I'll talk about production mechanisms, essentially how oil comes out of the ground, how you produce oil. I'll talk about the properties of the fluids, so you're producing oil, so what are those properties? And then I'll introduce a concept called material balance, which is simply keeping track of mass, but is a very powerful way to analyze production. Then I'll introduce fluid flow. Fluids are moving in rock underground, and there will be some analytical work, so-called Buckley-Leverett analysis and the analysis of imbibition. So those essentially are the main topics, and they will be covered in the lecture notes and in these series of lectures. But let's give an introduction, and let's start with first thing. Can you think of anything sitting in your room looking around that isn't made out of oil and gas directly? That is, it's not a plastic, for instance, or it doesn't have some fuel, or that oil and gas are used in its manufacture or transport. And in fact, virtually everything in modern life, not just one or two things. It's difficult to think of a single object that you might have that hasn't used the oil industry in some way, right? And most obviously simply empowering the manufacturing process, fueling how that product got into your house, for instance. So let's talk about the oil industry. I'm going to give you a brief history, a very brief history. For those of you who are generally interested, there's a fantastic book written by Daniel Yergin some 30 years ago called The Prize. Absolutely excellent book. So you can see the title. Actually, funny enough, the first environmental impact of oil production was quite positive, because hitherto the oil that was used principally for lighting had come from whales. And so whales were being hunted to extinction for their oil, and then petroleum came along and essentially replaced that. So that's a good thing, not, however, the last or the only environmental consequence, which we will be discussing later. So oil is found in porous rocks underground. Some of that oil does in fact exude to the surface. So for thousands of years, people have known this. There have been these natural seeps, and that oil, right, could then be used essentially as a fuel for lamps. However, the first sort of, let's say, modern way of looking at petroleum products, first of all, refining the oil. Crude oil tends to be a rather dark, viscous fluid. What you can do is you have a distillation process that separates out the lighter fractions that are most valuable as a fuel. So the first refinery was founded by James Young in Edinburgh, and you notice it's using shale oil. So it's in fact, shale is the source rock, is actually where the oil and gas are formed. Shale oil production, or the existence of oil in shales, is not new. What is new is the large-scale production of shale oil. But the idea has been around, as you can see, for 150 years. Then in Poland, it started distilling oil on an industrial scale. And as you can see, the guy whose name I'm not going to try and pronounce set up the world's first crude oil refinery, Poland, in 1853. So the distilled product was called kerosene, and that replaced displaced oil. But what about the oil itself? Right? We weren't relying on natural seeps by this time. The first oil well was drilled in Baku in Azerbaijan, near the Caspian Sea. That's in 1847. And in the 1860s, at the time we're talking about these first refineries, that was 90% of the world's oil was actually coming from Baku. But normally when people think about the oil industry, they actually think about the United States, and they sort of think, well, what about the history of the United States? So the first drilling for oil in the United States was by a guy called Edwin Drake. What they found was in Pennsylvania, there were water wells that were often contaminated with oil, essentially a natural seep. And so what they did was they actually did the first oil well by drilling down about 20 meters to strike oil. And they used the technology that was used in salt mines. Actually, they were genuinely drilling through the earth. So here is a picture of these early wells. You see there these wooden derricks. Essentially, those are the structures, right? And then the well goes through there, and the oil comes out. And you can see at the bottom, see here on the cursor, you see here, this is the oil being produced and just coming here on an open pit like this. Of course, we don't produce oil like this nowadays. Here are some other pictures, rather poor quality, I'm afraid. Here on the left is an oil field in California, and you notice here the wells are very closely spaced. There was a reason for that, is if you drilled a well and you struck oil, obviously you'd run around saying, yippee, I'm rich, you'd run into the saloon, and all your friends would immediately go out and drill a well right next to you to try and get as much oil for themselves as possible. So you had these wells very tightly spaced. Nowadays, as you can see, that's rather a silly thing to do. Nowadays, what happens is a single field is maybe owned by lots of different companies, but is operated by one company in order to maximize the production from the whole field. Okay. Most people associate, as I said, the oil industry with the United States, but more specifically with Texas. The first major discovery in Texas was in 1901, Spindletop. So there were some oil workers at the time of that discovery. So here I've simply taken from a book a brief history of the oil industry, and I'm not going to go through this basically word for word. The thing here, as you can see, a Model T Ford, the development of the oil industry in terms of producing oil, drilling and producing oil, went hand in hand, obviously, with the growth of the car industry. Right? What would fuel these cars? Okay, so normally people think about the car industry, Henry Ford doing the first mass production, but you do have to remember that would not have been possible if there wasn't widespread availability of a fuel. So the two things go hand in hand. Just a few things here. The large oil companies that you may be familiar with, Standard Oil, that was then split off, and Exxon, for instance, is one part of that. Shell, BP, these are all companies that were founded around the beginning of the 20th century, the early 1900s. It's also, for instance, when the first oil was found in Iran. The first major discoveries, say, in Saudi Arabia in the 1930s, and then it's post the Second World War that we had major production in the Middle East. Okay, so that's a history. This isn't really a history class, so I'm not going to say too much about it. But what is oil itself? Okay. The first thing that is actually, fun enough, easier if you're Italian as opposed to English is you sort of understand what petroleum is. Petroleum, right? Petra simply means rock, oil. Okay. Crude oil, again, in English, crude is normally meant to mean vulgar. Okay, so again, it doesn't seem to make much sense when you talk about crude oil. Again, in Italian, it does crudo, so it simply means uncooked. Okay, so crude oil is all that directly comes from the reservoir that has not been refined. Okay, so it's a mix of hundreds, thousands of chemical components, but mainly hydrocarbons. Hydrogen and carbon mixed together in branched chains. You also have arenes, which are essentially compounds containing benzene rings, so rings, and you do have some other components. There can be sulfur, carbon dioxide that you have to separate out, and other trace components. Crude oil in general is black in color, or when diluted or spread out is sort of orangey. The reason for that is essentially because of these complex branch chain molecules have absorbed the light. Refined oil, if you think about petrol that you might put in your car, shorter chain alkanes, and that's a colorless liquid. So where does the oil come from? Right? It's funny enough, it is a natural substance, and it's formed over geological time from the partial decay of marine organisms, normally shallow marine organisms, so plankton. So it's essentially organic material. Now, you might say, well, when plankton dies and maybe sort of settles down to the seabed, then bacterial activity sort of eats it up. That's true, but if it doesn't completely decay, then what happens is you form a substance called kerogen, which is organic material. So when we talk about shale oil and gas, that shale, right, is a sedimentary rock that contains this kerogen, essentially the source of gas. And then what happens is over geological time, so the marine life goes to the bottom of the seabed, there's then deposition of various materials. One of the obvious materials here is if you have creatures with shells, right, that's calcite, right, it's the same material as chalk, that's what chalk is. Then of course you're depositing rock plus these organisms. And then if it gets buried at sufficiently high temperatures and pressures, that kerogen is converted chemically to oil and gas. And the higher the temperature, the further the conversion goes. So you form oil in a temperature range of about 50 to 150 degrees C, and you form gas in around 150 to 200 degrees C. So essentially, as the deeper you go, the hotter you go, you tend to get lighter and lighter hydrocarbons. You're more shallow, then those hydrocarbons tend to be heavy. So I did mention a little bit about the rocks, okay? So many sea creatures, as you know, have a calcium carbonate shell. So those shell fragments, essentially, the source material of most carbonate rocks. So for instance, in the Middle East has been a sort of shallow marine environment for the last 600 million years. And it's been depositing calcite and calcium carbonate throughout that time. So you have these huge reservoirs, essentially, of calcium carbonate. Okay? With carbonates, sometimes the rock actually looks like it's formed of shells, but it's highly reactive. So that calcium carbonate can, again, over geological time, it can react, it can dissolve, it can reprecipitate, it can actually change its chemical nature. So you get a wide variety of pore structures. And so the oil, which originally is in relatively tight shale rock, because it's been deposited at the time, you know, creatures died and then buried deep underground. Then when it forms oil and gas, that oil will come out of the shale and tend to move upwards, and it will move upwards through porous rock that has been deposited subsequently. It's moving upwards. So you find oil and gas in what are called technically porous media. Porous media, essentially, any type of material that has holes. Okay, so what we have here on the left is a schematic, right, of a grain with a restriction between them. What's shown next to it is actually an X-ray image. It's in fact a three-dimensional image, but I showed it in cross-section of a piece of sandstone. So the other major sedimentary process is with sandstones. Here it's silica, so it's the same material as glass, but in grains. And again, sand can be deposited in many ways. One of the classic examples is, for instance, the Gulf of Mexico. So offshore Gulf of Mexico is another major oil province. That's mainly sandstone. Why? Because you have the Mississippi. If you've ever seen the Mississippi, it's quite turbid. What it is it's wearing down the Rocky Mountains, more or less grain by grain. And all of that material has been dumped out into the Gulf of Mexico. So you have an enormous deposition, essentially, of sand. So you can have a sandstone. So this is Bentheimer, is actually a quarry sandstone. It's a sort of sandstone that's used for buildings, in fact. So what you find is you've got the grains. These grains could be calcium carbonate, the remains of shells. They can be sand grains. They can be whatever. And what you find is that because they've been now buried deep underground, so quite crushed together, you find about approximately around a quarter of the total volume of the rock is this void space. But this void space does tend to be connected. Okay? And the oil, gas, and water, because naturally these rocks are water saturated. If you dig underground, the soil becomes water saturated. If you're beneath the sea, it's obviously saturated with water. So initially you're saturated with water, and then oil and gas can enter the pore space as well. So you can potentially have oil, water, and gas in these tiny pore spaces that you can see are of a scale of sort of around a micron to tens of microns, so sub-millimeters. So here are just some illustrations so that you can see what rocks look like. So here is what's called Estiolades. Estiolades is a limestone, so it's principally calcium carbonate. You can see rather complex structure. That's also the three-dimensional picture here. Again, it's a quarry sandstone, so it's used for building. Keton is another one. It's got these sort of balls here, and these are actually sponges, maybe the wrong word, but they're microporous balls. It's called an oolite. This again comes from a quarry. We look at these quarry rocks because they're standard. You can take one piece of rock and then the next piece of rock is similar, and that's why they're used in building material. Keton is used in sculptures. We carve it in lots of different directions. Here's Mount Gambier. As you can see here, this rather open, complex pore space. You can almost imagine you can see the original fossils, the original shells there. There's a sand pack, which is just sand packed together, obviously. Bentheimer, which is, again, a sandstone. Portland limestone is, again, another carbonate. It's used very much in Britain for buildings. So some of the most prestigious buildings in Britain are made out of Portland limestone because it makes a beautiful white facade. So for instance, the building where I work, the Royal School of Mines at Imperial College London, that's made out of Portland stone. Okay? And we've got gritting, which is another limestone. And then here's a carbonate from the Middle East, which is top secret. So I can't really say anything about it, but you can see that has a rather complex and rather tight pore structure. Okay? But there will be, not in that sample exactly, but there will be oil and gas in those types of rock. Then this course is going to be about how do we get this oil and gas out of the rock. And for that, we need to understand the fluid flow and the pore structure. So here, just for an illustration, because we will be developing this idea later, is what's shown at the top is not an image of the rock itself, because in fact, we're interested in what happens in the void space, because that's where the oil and gas is. So this is an image where I've actually shown the void space, right? And so you can see you get this complex void space here. But Keton, you can almost imagine, you see the things that are left out of the sort of spherical, almost spherical grains. Beneath there is what's called a topological or network representation of pore space, where the balls are where there's a wide area in the pore space. And then the wide areas are connected to another wide area via a restriction that we call a throat. Okay, so the pores, the wide areas are represented by the balls, and there's a sort of link, right, shown here, which is your throat. So if you think about flow and porous media, this is at the sub-micron scale. It's like moving in some complex network from ball to ball. And you can see Mount Gambier, which was this open structure with all these shells looking very complicated, its pore space is very open. So you can see there it's actually quite easy for things to flow, for things to move from place to place. Keton isn't too bad because it's got quite a regular pore space, but Estiolades, which had this very, looked sort of complex structure, is not very well connected. So it's got lots of little pores and not very well connected. It's going to be much more difficult for you to have fluid. Okay, so that was the small scale. That was the sub-millimeter scale. What about at the large scale? So these diagrams, we're now looking at the scale of several kilometers. So we may be looking at sort of 5 kilometers across here. So what happens is, as I said, the marine organisms, go to the bottom of the sea, there's further sediment piles in. You tend to have this rather low permeability shale, as I said, and buried deep underground. So that's where the oil and gas are formed. When that oil and gas is formed, so the kerogen converts into oil and gas, this oil and gas can move upwards through the rock. Okay, so it tends to do that, tends to move into more porous rock. So conventional oil and gas fields are actually oil and gas that are contained in the sort of rocks I've just shown, as opposed to production directly from shale, which is obviously now happening in the United States, which is actually going directly to the source rock. But that tends to be lower permeability, and that's why you have to fracture it to sort of break up the rock to allow the flow. So if we look at traditional oil fields, then we have something like this. The gas is shown in red, right? Gas is less dense than oil, so it floats above the oil, obviously. The oil is shown in green. And then what's called here is this is water. So the porous rock will naturally contain water, okay? Salty water if it's deep underground. The oil and gas will obviously float above there, but remember it's in rock. It's not a cavern underground, it's in the rock. Okay? So it's contained within these sub-millimeter pore spaces. So an anticline is where you have essentially a dome shape. So you have some rock that is impermeable, that doesn't allow flow or doesn't allow much flow. So it could in fact be more shale, right, which actually doesn't allow much flow. It could be a salt, which is shown here. Anything that's, or a clay, anything that doesn't really allow significant flow. So you can have an anticline, you could have a fault. So through tectonic motion, the ground moves, and then that fault sort of gets sealed up. There can be precipitation reactions that essentially seal up that fault. Or as shown here, you can have salt. Salt, incidentally, I mean, you know how salt is deposited. Essentially, you evaporate the sea. Salt over geological time will move. It's actually sort of almost semi-fluid, so it tends to get squeezed up into form this dome, and this forms an impermeable barrier against which the oil and gas works. So just to get some scales here. So what about temperatures? Naturally, as you go deep underground, things get hotter. So we have a temperature gradient of approximately about 30 degrees C. And we're normally looking at reservoirs that are a few kilometers below ground. So the temperatures we typically encounter in a reservoir, somewhere in the region of about 100 to 150 degrees C, something in that order of magnitude. Now, if we look at pressures, okay, you know how to calculate pressure, rho GH, right? Density times acceleration due to gravity times height. In a porous medium, it's no different, right? If you imagine you're in the pore space of the rock, and you have a passageway all the way to the surface through rock, you essentially see the pressure of the fluids. And that's something we're going to talk about in more detail in the lecture. It's rather important. But if you think about, say, your kilometre depth below the water table or below the sea, the density of water is about 1,000, okay? G is about 10, okay? And 1 kilometre, so that's 10 to the 7 pascals. Just for reference, atmospheric pressure is about 10 to the 5 pascals, 100,000 pascals, 100 kilopascals. So we're looking at hundreds of atmospheres. We're a few kilometres below ground, we're looking at a few hundred atmospheres, a few tens of megapascals. One thing you notice immediately, obviously this isn't a precise calculation, it's just a slide, is that I'm using here SI units. So I know traditionally in the oil industry people use what's called field units, even sometimes even British units, but actually I'm going to do everything in SI units. We are going to introduce field units later, but I don't have to do it straight away. So here's a picture here from the Encyclopedia. It's okay, but it sort of has the reservoir rock dissolve away where the reservoir is. That's completely incorrect. Okay, it is all rock. So you've got a cap rock, which is this impermeable barrier that stops flow. There's a gas cap. There's the oil. Okay, and there's essentially salty water here. So you're drilling through here to produce the oil and gas. So I did mention shale oil as well. So one of the major developments in recent years has been a huge amount of additional oil recovery from essentially the source rock. And so here's a map of the United States, and shown in green is essentially where the shale is. And it's a huge, absolutely enormous resource, but it's very low permeability. So said you have to fracture the rock to allow flow. Now we'll look back to conventional oil. Where do we find oil in the world? What are some of the biggest fields? So here's just a list of some of the biggest fields in the world. Number one is Ghawar. That's in Saudi Arabia. Okay, as you know, Saudi Arabia is one of the largest oil producers in the world. The three largest are the United States, Russia, and Saudi Arabia. Okay. So Ghawar is a huge field, as I said, started going on production after the Second World War. It produces about half of the oil that Saudi Arabia produces in total, and it probably has almost 100 billion barrels of oil that is recoverable. You might say, just a moment, you said you're using SI units. What's a barrel? Okay, a barrel is, and you can look it up, right? This is what I suggest you just Google it if you want to know the conversion. In the early days of the oil industry, oil was sold in barrels. Okay, so it's just become standard. So everyone talks about oil volumes in barrels. Barrel they're about 6 barrels to a cubic meter. It's about 169, I think, litres. Okay, so if you want that in cubic meters, you just divide by 6 approximately. Okay. So the next largest field is the Bagan field, which is in Kuwait. So again, in the Middle East. This one actually is principally a sandstone. It's the world's largest sandstone reservoir. Okay, and then you can see large fields in Iran, Brazil, Mexico, Venezuela has huge resources as well. You can see a big field in Kazakhstan and Russia. So you go down that list, you get to, one would say, the bottom of this page before you see the first field actually in the United States. So that's Prudhoe Bay, that's off the north slope of Alaska. Okay. Now, to put this sort of in perspective, you look at these fields, you can put some money to it. Right? The oil price at the moment, largely because the economy, the world's economy is looking a bit wobbly, is about $50 a barrel. So that's considered reasonably low. Okay, and we're looking at these fields that all have at least 10 billion barrels. Okay, so that's if it's 10 billion barrels, that's $500 billion, right? And most of these, if you say it's 20 billion, that's $1 trillion right there. Okay, so you can see these fields are enormously valuable. So you might say, well, the oil and gas is underground. How do we know it's there? So the oil industry, until sort of a generation ago, was very much focused on finding the oil. In fact, people still sort of view the oil industry like this. You go around finding oil. Oil men, right? People decide, to make the oil industry as sexist as possible. Of course, that's nonsense. Women clearly work in the oil industry like they do in any other industry. But anyway, you have these people going out and finding oil. Okay, so this is the main thing. So how on earth do you find this oil? So it used to be that it was fairly obvious. You look for the oil seeps, right? And then, well, obviously there's oil down there. But the first time people sort of put a bit of geology into it was, in fact, what's called Teapot Dome, the Spindletop discovery in Texas, where it was a dome. And you saw a dome shape, and people thought, aha, maybe this is an anticlinal trap that stores oil and gas underneath. Okay? So that was looking at a surface expression, but most of these fields are, as I say, kilometers underground. So what you do is you use seismic surveys. You essentially send sound waves into the rock, and you look at the reflections, and the reflection back basically gives you an image. Essentially, you have a reflection where there's a change in rock properties. So you can see, for instance, the existence of a potential cap rock. So what you do is you use explosions or vibrations or air guns to create sound waves that then travel underground. Okay? And those produce a three-dimensional image. And here is an example. An engineer next to a big projection of a three-dimensional images, and these are the layers. And what you're trying to do, the layers of rock, and what you try to do is you identify a place where oil and gas might be trapped. Okay, and then you also use some geological inference to say yes, there may be source rock below them. Okay, so this is a huge industry. You use very sophisticated equipment to make these seismic signals, and then an enormous amount of computer power to basically produce the images that you see. Okay, so you can do this onshore and offshore. Onshore, essentially, you've got a truck there, and you can see it's got a big thing that goes bang, 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 and then you have microphones that essentially record it. But enough, offshore, it's easier. You have a boat with what's known as streamers, and they send vibrations underground, and then you have this big, this can extend several kilometers. So here's an example. Here's the boat. It will be sending sound waves actually go through the ocean quite efficiently and then through the ground surface. Okay, and these are the microphones that are then picking up the reflections. And from that, so you imagine you send out a signal, it goes under and bounces back. You can measure the time, and if you know the speed of sound, that can give you a distance. And so you can actually say, okay, I've got this layer of rock this deep underground. So that's seismic surveys. And that enables you to identify where potentially oil and gas may be trapped. It's quite difficult, though, to detect the oil and gas directly from sound waves. There is a slight difference in the speed of sound, particularly if you have rock filled with gas as opposed to water, but it's often not significant enough for you to know for sure it's gas. So you have to drill. So you drill kilometers underground, and you go through hard rock. Okay. So the teeth, the thing that is actually cutting through, is called the drill bit. You'll notice in petroleum engineering, we tend to use not these long, fancy Latin words that people often do to sound pretentious and well-educated, but actually short words, but they do have technical meanings. So a drill bit, the bit is the teeth. And that obviously has to be very tough. And remember, we are going into an oil reservoir potentially, which is worth a huge amount of money. So often you have super tough steel, but you also, in fact, have diamonds, industrial diamonds. They're not necessarily for jewelry, but they're the hardest thing we know. So they can go through the rock. And then you have a drill string, right? It's not literally a piece of string, but it has to be a connection to surface so that you can direct the drilling. And it normally takes a few months to drill. So here is an example. These are your drill bits. You notice some of them, just sort of whirl around and go through the rock. Some of them seem to have a hole in the middle. There's a reason for that. The oil and gas is contained in rock, and we want to understand what's going on, what that rock is. Okay, so if you have a hole in the middle, you can actually extract in the middle what's called a core, right, the center piece, and that's your rock from the reservoir. Okay, so you can take that rock to the surface, and you can analyze and look at the flow properties and predict what's going to happen. So that's really rather important. So here we have, this is offshore. Okay, we've gone deep underground here, and you can do directional drilling. So drilling in the modern world has become very sophisticated. You can direct exactly where the drill goes, related to your seismic survey where you think the oil and gas may be. Okay, and this will extend several kilometers. So you can go several kilometers deep and several kilometers laterally when you're drilling. Okay, so how do you drill? You start with a wide hole, and then you've got to be careful because as you go below the water table, if you're under the sea, obviously this hole is going to fill with water, and also it might collapse. So what you do is you drill a wide hole, and then you put a casing, which is basically steel, down there, and then you drill within that. So the holes get narrower and narrower as you go down. Okay, so you start maybe with a diameter of about 1 meter, and then you go down to a diameter of probably around 10 centimeters. Although again, here people always quote well diameters in inches, I'm afraid. So it's about 2.5 centimeters to an inch. Okay, so you have this cascade of smaller holes. Okay, so the rock in general, as you drill, it's crushed into small cuttings, and then what you do is as you're drilling, you're lubricating and surrounding everything with what's called a drilling mud. Again, mud, fango, is not, literally mud. They're not putting earth in the well. It is a technical expression to describe a dense mixture of fluids. It's dense because you want to maintain pressure. And we'll explain that later. It's going to cool the bit, and it's going to help bring that rock to the surface. So you're basically circulating this mud. Okay? And the mud could be based either water or oil with things dissolved in it to make it dense. Okay, so you can cut in an annulus, as I've just said, to extract these cores, which are the rock samples. You can also extract cores actually sideways. You can drill a little core sideways in the hole. This is called sidewell cores. And you can also extract the fluids. Right? So when you get to the oil reservoir, if there is oil, okay, oil will start coming into the hole, and you can extract that. And you can measure then the properties of the rocks and fluids in the laboratory, and that is actually rather essential to know what it is you've got underground. So what's called an open hole is where you just basically have a hole in the ground. Okay, so there's no casing. Obviously, you can't really persist with that. So what you do is the drilling proceeds, you insert steel piping in that hole and maintain stability, and it prevents water coming in. And then cementing is where you essentially use cement between the steel and the rock to hold the casing in place and to prevent essentially the uncontrolled release of fluids. So here's an example. Okay, so here we have the cascade. It's not to scale here because you've maybe go several kilometers. And here you can have some sort of expandable tubing, and there's lots of very sophisticated technology here. Here you have the diameter here, 36 inches is okay, and then you go down to about 7.5 inches. So we're looking at about 20 centimeters here. Then you can take measurements, so you can take out the fluids, you can take out the rocks. Obviously you can analyze those in the lab, and that's going to be important. We can talk about that later, but you can also actually make measurements down the hole. Those measurements are called logs. Again, another short word. It's nothing to do with a bit of a tree. Okay, so it's not that type of log. For those of you who are Star Trek fans, you might hear, Captain's log stardate. You might say, well, what's this log? Log is an old-fashioned word actually for recording. Okay, so I used to have a captain's log in a ship, which was simply the captain recording what's going on. So when we call these log measurements, they are in fact simply recordings of things that you measure underground. So the oil industry actually noticed this, a lot of things in America, actually using quite archaic language, strangely enough. Okay. Unfortunately, you can't really get direct measurements of the things you want, like flow properties or the fluid properties, but you could infer things. So you can measure, for instance, electrical resistivity. You can send a current through the rock. You see how that behaves, and that tells you what's in the rock, because brine, water, conducts electricity, and oil and gas don't. Okay? So if you measure resistivity, what you find is, as you're going through water-saturated rock, resistivity is low, there's little resistance, it conducts for electricity. And then if you hit oil and gas, this resistivity is much higher. So it's a signal that you've got hydrocarbons. And in fact, you can actually quantify this. What fraction of the pore space is occupied by water? It's Archie's law is one of the key developments in sort of quantifying and getting numbers out from these measurements. Okay, so that's used to say how much water is in the reservoir and how much oil and gas there are, and to detect where you find oil and gas. The other thing you can do is you can have neutron or gamma ray. Essentially, there's a measurement of density. Essentially, how much does the rock absorb these gamma rays or neutrons? So it's a measure of density. And so what it can do is it can measure, obviously it's absorbed by the rock more strongly than the pore space. So it can use to measure the porosity, the fraction of the rock that is void space. But it can also tell the difference between gas, because gas is much less dense than water or oil. It can't really tell much between water and oil because they're similar density, but it can use to detect the transition from oil to gas. Okay, so here are some examples. Okay, here's gamma rays, essentially looking at density. So where it's shale, rather dense rock, low porosity. Where it's sand, there's a more porous rock, so you can immediately identify there's an area here. So this one could be a trap. This doesn't allow much flow. Not all shale contains oil and gas, right, as the source material. Most shale is just low permeability rock. Okay, so here's the sand, which is high permeability. So this is potentially where oil and gas could be trapped. Then you look to the resistivity, and the resistivity is high here and low here. So we know that it's hydrocarbon here, okay, brine here, but we can't tell the difference between oil and gas. But then if we look at neutron porosity, we do see there's a difference between the absorption of neutrons, gas, oil and water. And you can see here, this is a less dense material here and more dense. So you can now identify that this is gas, this is oil, and this will be rock. And then there's a shale here that prevents the hydrocarbons escaping upwards. So once the well is completed, in fact, the way of doing this safely is you drill a hole, you put in your steel, you cement it in place, and then, to begin with, there should be no flow. Okay, this is how to do things safely. You have essentially your hole and it's completely isolated. Then what you do is you put controls at the wellhead to prevent excessive production and to deal with the production of fluids. Okay, and so you have what's called a blowout preventer. If there is an unexpected release of fluids at very high pressure, essentially you seal off the wellbore. You have at the top of a well what is something that looks like a Christmas tree. So again, another technical thing, we don't put trees on the top of wells. A Christmas tree essentially has lots of pipes and valves. Essentially, it's to have the controlled release of fluids. So you want to stop production. So how do you stop production in a controlled fashion? You actually shoot bullets through the casing, okay, where you think they're hydrocarbons. Okay? So that makes a hole, and those holes are called perforations. Okay? And then you have the fluid flow into the wellbore. And that is the safe way of doing it. The problem is that when you were drilling the well, right, you're keeping everything at high pressure, you're creating these cuttings, and these get forced into the rock, right? And now you sort of try to blow a little hole through. You often find that formation of the rock essentially is clogged. So what you can do is you can inject acid to try and dissolve it away, or you can inject water at very high pressures that sort of fracture the rock, hydraulic fracturing. Now, this is another interesting thing here. Until recently, when hydraulic fracturing was something only known to the oil industry, it was called hydraulic fracturing, right? We use this sort of Greek Latin expression, right? That's a sort of respectable technical expression. When the production from shale, which can only happen because you fracture the rock to allow flow, came, people couldn't deal with the fact that the oil industry, strangely enough, was actually using a technical expression like any other respectable industry or any other science. And so, well, that wouldn't do, would it? So, surely in the oil industry, people are using something that sounds a bit more Anglo-Saxon. So fracking was made up. Okay, it wasn't. It's not a technical expression that was ever in use in the oil industry, but now, anyway, it's become common. So we call it. Okay, so here is an idea of what it is. I mean, you can fracture the rock if a conventional well, because it essentially forces the rock apart and allows the fluids to flow more easily. But it's absolutely essential if you're doing it in a shale formation. So in a shale formation, you drill a horizontal well like this, and then you force in water and sand at very, very high pressure. So it pushes the rock apart. You create a fracture that tends to be in a plane that's perpendicular to the well. So it's vertical now. You inject water, obviously at high pressure, because that forces the rock apart. You also inject sand. The reason is because, okay, you inject water at high pressure, but you won't actually produce oil and gas. So you've got to drop the pressure and allow oil and gas to come. So the fractures will just close again. So that's not terribly useful. So the sand is essentially what's called a proppant. It goes into the fractures right, and props them open. So when the pressure goes down, the fractures don't collapse again. Okay? And then there are other chemicals, right? And the other chemicals are essentially to allow the fracking process to occur as efficiently as possible. But obviously, that comes with some environmental concerns. So you have to make sure that you inject this water, it doesn't escape anywhere, and then you reduce it back and dispose of it safely. Okay, so now we have the oil and gas. Okay, we start producing it. What you find, and this is this schematic, you may have oil in the reservoir and you may have gas. When gas comes to the surface, normally the gas expands, okay, because it's at high pressure, hundreds of atmospheres pressure, so it will expand actually so 100-fold. On the other hand, oil, again, is at high pressure, and it's a mixture of hydrocarbon components. And as you drop the pressure, the lighter components, basically methane, ethane, propane, and butane, as well as CO2, will come out of solution. So you'll produce oil and gas at the surface, even if you've just got oil underground. So basically what happens is the fluids flow into the wellbore and upwards, right, under pressure. Okay, you have a turbulent flow where you have basically oil and gas mixed together. You can boost the flow rate artificially. It's called artificial lift that essentially encourages that flow with pumps essentially, or using gas, right? Basically bubbling gas through the wellbore that keeps everything loosed up. And the oil and gas are separated at the surface, and you design that actually to get as much liquid as possible. And then the oil is transported by tanker or pipeline. Okay, so we can produce both onshore and offshore, essentially below the sea or below the ground. The main thing here is cost. Okay, onshore we can drill a well for normally a few $1 million. Offshore, the drilling of the well can be much more expensive just because it's much more difficult. You have to have an offshore facility, and so this can cost a couple of hundreds of millions of dollars. Okay. Offshore, our technology is getting better and better. We used to have platforms that are actually stuck in the seabed. Now we can have things that are essentially floating and tethered to the surface, and we can start producing oil and gas now. Used to be a few hundred meters depth, but we can now go to kilometers depth of the sea and then several kilometers below there to access the oil and gas. We can also produce directly from the subsurface. So actually here's a field offshore Norway. You don't see anything at the surface. So you produce at the seabed, and then you have these pipes that will run everything to shore. Okay, so I'm going to pause now. This is going to be the end of the first lecture. In the next lecture, I will say a bit more about how oil is produced. So this was just an introduction. I hope you found it interesting. You do have access to those slides, and you can read some of the lecture material. Okay, thank you very much.